Welcome! We are going to do section 11.5 today, lines and planes in space. So the objectives are to be able to switch between parametric equations of a line in space and some characteristics of the line, so vectors along the line, points on the line, etc. And switch between the linear equation of a plane in space and characteristics of a plane. So similarly, if we have an equation, what vectors can we find that are in the plane or perpendicular to the plane? What points can we find? Are there any angles between the plane and maybe the xy plane that we can look for, etc. Sketch lines and planes in 3D, well, on the paper, but to mimic 3D, and then calculate distances between a point and a plane or a point and a line in space. And then, of course, we need to adapt these formulas for different problems that we may encounter. So a note to start with is that in the plane, we define a line with a point and a slope, typically. In space, however, that's not quite enough because the slope doesn't define it exactly. There are many lines going through one point that have a specific slope. What we need is a point and a vector. We call this vector a direction vector. So we can see that a point is also what we needed in 2D, and then the vector acts as a slope. In fact, a slope, really, you can say it's a special vector. It's just, if it's slope m, then you could express it with the vector 1m in any situation. So a slope is almost like a vector in 2D. So how do we express lines? We define them with parametric equations. X equals x1 plus at, y equals x2 plus bt, z equals x3 plus ct, where x1, x2, x3 are the coordinates of a point. And then vector v is abc, it's a direction vector, so it goes in the direction of the line. So you can see how if you choose t equals 0, the parameter t equals 0, that will give you the point x1, x2, x3. If you choose, for example, t equals 1, it'll give you another point that goes one step away from point x1, x2, x3 along vector v. Here's an example. Find a set of parametric equations of the line going through P205 and Q43, -1. Find two other points on the line. Okay, so we need a point and we need a vector. We are given 2 points, so we'll pick one of them. Let's say we pick P205. And then to find a vector that is along the line, a direction vector, we'll just take the vector PQ. And that is 2, 3, -6. It's written here. So easy breezy. Here's the parametric equations of line L. X equals 2 plus 2t, y equals 0 plus 3t, and z equals 5 minus 6t. So vertically you can see the point 205 and the direction vector 2, 3, -6. So how could we find two other points on the line? All we need to do is to pick a certain value for t. If we did pick t equals 1, we would get point q, actually. We would get 4, 3, -1, right? So t equals 1, we can't choose that. We can choose t equals 3, which yields 6, 6, -7, or t equals 2, t equals 3. We could choose t equals -1, which would yield point 0, -3, 11, and so on. T equals 0.5, or whatever you want. If you choose all the values of t, then it defines the line in space. Notice how parametric equations of a line are not unique. Firstly, we could have just chosen point q instead of p, so the same line can be defined as x equals 4 plus 2t, y equals 3 plus 3t, and z equals -1 minus 6t, just picking q instead of p. And we can also choose a different direction vector. We could have chosen the vector qp. We could have chosen the direction vector 5pq, whatever. So what this means is that be careful in exercises if you're solving a problem and your neighbor in class is solving another problem, and you look at and you ask what is the value of t, you may all have different values of the parameter because you've picked a different way of defining the line. So interestingly, in space, to define a plane, one would think that you need a point and then you need two vectors inside the plane. That would define the plane indeed. But actually there's an even better way, which is really clever, and that is to use the normal vector. If you have one point and you have one normal vector, there's only one plane that is defined by them. So the standard equation of a plane is given here. It's a times x minus x1 plus b times y minus y1 plus c times z minus z1. x1 is a point in the plane, so these are constant values, they don't change. And abc is a normal vector. So how come this works? And it's going to be incredibly important and useful to keep in mind that when you have the equation of a plane, you can immediately read the normal vector. It's a, b, c. It's the factors of x, y, and z. So how come that works? Well, if x1, x2, x3, or xp, yp, zp, as it is written here, are defining a fixed point in the plane, and if we know that n is abc, then all the points in the plane, all the points q in the plane are such that pq.n equals 0. So if q is here, for example, then this vector pq is perpendicular to n. So this is going to be true for any point q that I choose in the plane. So that means I can say pq.n equals 0. This gives me a way to define what's special about q. And so if I take the dot product of these two vectors, vector pq and vector n, I immediately get the standard equation of the plane. It's quite nice. The general equation of a plane in space is given like this. It's the same, except we have a d now that appeared. And so what happened? We just distributed it. Ax minus ax1 plus by minus by1 plus cz minus cz1. So we can gather all the constant terms and put them in one constant d. So d equals negative ax1 minus by1 minus cz1. So let's see an example. We are given 3 points, p, q, and r, and we are interested in finding the plane that goes through these 3 points. So we will need a point. We have a wealth of points. We'll just remember to use one of them. And then we need a perpendicular vector, so a normal vector. And to do that, we will, of course, use the cross product. This is really essential. The cross product is essentially used to find perpendicular vectors in space. So PQ and PR are one option we have to find two vectors in the plane, 2, 3, negative 6, 0, 2, negative 5. So the normal vector is going to be PQ cross PR, or it could be PR cross PQ. You would just get different signs. But in any case, here we get n equals negative 3, 10, 4. And therefore, we have the standard equation of the plane immediately. Notice the negative 3, 10, and 4 show up here. And then we just need to pick one of the points. So we chose point P. So it's x minus 2, y minus 0, and z minus 5. Find two other points in the plane. You can do it. There's infinitely many options. The easiest way to do that is just to pick x equals 0, y equals 0, and you'll get a z in order for this equality to work. Or then you can pick x equals 0, z equals 0, and that'll give you another point. Or you can also, of course, choose x equals 2, y equals 5, and then calculate the value of z that is required to make the point in the plane. when you have two planes, there's really two options. Either they are parallel or they intersect. When they are the same plane, we consider that to be part of being parallel. So if they intersect, then the intersection is a line. And we can be interested in finding what the angle between the two planes is if we measure it along the line. And to do that, instead of thinking about planes, we might as well think about the normal vectors. Here's a nice illustration of n2 being the normal vector of the purple plane and n1 being the normal vector of the blue plane. We will measure the angle between n1 and n2 rather than between the planes themselves. This is the same illustration. It's also very nice. It's viewed if you were looking from here. So you don't see the planes because you are kind of aligned with the plane. So this is the purple plane, and this is the blue plane. You're looking right from the line of intersection. So it allows us to sketch N2 and N1 quite nicely and to see what happens. So the example here is a really neat example. I don't know why there's these two lines. This is a very neat example, and it's a great exercise, not easy at all to figure out how to solve it. So find the equation of the line of intersection of the planes given by pi1 and pi2, as well as the angle between them. To find the equation of the line of intersection, what's interesting is we're going to have to figure out how to find a point, and then we're going to have to find a direction vector. So the recipe is given here: find a point on the intersecting line, and then find the direction or a direction vector of the line. And once we have that, number 3 is easy. What's not easy is to figure out how to find a point on this intersection line. How do we do that? There's so many options, and it's not quite clear how we're going to go about doing that. There's actually many ways you can do that, and I think just playing with these two equations until you figure out a point that is on both planes is a fine way. The way I chose to do here is that I just set up x to be 0. So it suddenly changes this to 2y plus z equals 0, and then 3y minus 2z minus 2 equals 0. Why can I just choose x equals 0? Because there's infinitely many options of points on the line. I can see that I have 2 equations, but I have 3 variables, so I can just pick one, and then it'll leave me still 2 to solve. And if we do that, we get the point 0, -2, -4. It's on both planes. We can check by plugging in here and plugging in there. So since it's on both planes, it means it's on the intersection line. Step number 2 is to find the direction vector of the line. That's not obvious either, but a great idea is to remember we have normals to each plane. We have n1 perpendicular to plane 1, and we have n2 perpendicular to plane 2. And what happens is the direction vector is perpendicular to both of these vectors, because the direction vector must belong to the plane, to each plane. So by definition, it's going to be perpendicular to the perpendicular vector. So by using the cross product, we get a direction vector. So D equals n1 cross n2, and we find 1, 4, 7. From here, it's very easy to solve the problem. So let's continue with the second part of the problem, the angle between the two planes, and it's going to shed light on a little subtlety that is involved in calculating this. And the subtlety is the angle between two planes can never be more than 90 degrees. If you imagine, for example, these two planes down here, if you think of this plane kind of slowly moving in a counterclockwise direction, when it reaches an angle of 90 degrees, then we would measure the smallest angle always, so the angle would start decreasing. Instead of the angle being on that side here, it would start being the angle on this side here. So what does that tell us about the formula that we've studied between two vectors, the angle between two vectors? What changes is we have to take the absolute value of the dot product of the two vectors. That will prevent cosine theta to be a negative number. Let me just think. Yes, it will prevent cosine theta from being a negative number, which would actually give angles that are all the way up to 180 degrees. So two vectors can have angles between them that are up to 180, but two planes, it's limited to 90. So here's the calculation, and careful, we need to have absolute values. So we know n1 is 1, negative 2, 1. It's amazingly easy to find a normal vector to a plane. n2 is 2, 3, negative 2, extremely easy. And therefore, we can just plug in everything in the formula for cosine theta, and there we go. Cosine theta equals 6 over root 102, which yields an angle of 53 degrees or 0.935 radians. We're now going to talk about sketching, and in order to sketch in particular planes, we have to introduce the concept of trace. And the trace is the intersection of a surface, any surface, with the three coordinate planes. Because when we sketch surfaces or planes in particular, we are only going to focus on octant 1. Now, some of these would not ever show up in octant 1, but of course the examples we'll pick for class convenience are going to. So here's the first example. How do you sketch the plane 3x plus 2y plus 4z equals 12? What we're going to do is to look at all the intersection with the axis. So if we want to find where the plane intersects the x-axis, what's special about that is that y equals 0 and z equals 0. So we set y equals 0, z equals 0, and we find, just looking at that x equals 4. So we know the plane goes through this point here. We repeat the process for the y-axis. So we set up x equals 0 and z equals 0. We find y equals 6, because 2 times 6 equals 12 up here. And finally, doing the same for the z-axis, we find z equals 3. Now, because it's a plane, it's easy to sketch the traces. It has to go straight from here to there, and back up here. I hope when you see these three red lines, you can kind of see the plane. Everything else about the plane is behind the 3 xy plane, yz plane, and xz plane, but this allows us to kind of visualize where the plane is and what its kind of orientation is. Let's look at another example where we don't have y here. So what does it mean? What it means is that you're not going to have a y-intercept. We can still do an x-intercept. We set up y equals 0 and z equals 0, and we get x equals 6. So same as before. For the z-intercept, we set x equals 0 and y equals 0. There's no y. We get z equals 2. And now y, well, there's no y-intercept, and what that means is that the plane is parallel to the y-axis. So after drawing the line between the two intercepts we found, we have to carefully draw lines that are parallel to the y-axis to show that it never intersects the y-axis. And finally, a further example where we now only have one variable only, x is absent, z is absent, and you just have y equals 4. What does that mean? Well, that means y equals 4, and that's it. So all the points on this plane here that's shown with these two traces are points where y equals 4. So for example, you would have the point 5, 4, 9. That's a point in the plane, and indeed y equals 4. So there's many ways of sketching traces. Here's an example. I didn't look for an equation, but that would be a valid trace for a certain plane. So this one will go down and eventually it will hit the xy plane, but it happens behind the first octant. Lastly, we're going to talk about two distance formulas, and here are the formulas, so you'll have that in quizzes and tests, but I'm going to switch to the iPad because I want to talk a bit more in detail about how we get these formulas. So let's talk a little bit about how these two distance formulas came to be. These are two wonderful little proofs that tie what we've studied in previous sections and some visuals. So when we are looking for the distance between a plane and a point, the point is of course outside the plane or else the distance is 0. First of all, what we talk about is always the shortest distance. So it's the distance that will, once it hits the plane, make a right angle. So we are looking for this distance here. To do that, we're going to want a point, any point P that is in the plane, and we're going to use the vector PQ. So remember, we are looking for the distance that is the shortest distance between Q and the plane, so it hits somewhere here. So we have another vector that we always know, and that's the vector n. Now notice that the distance I showed on the right can also be represented on this side here. It's something like that, like this. It kind of forms a rectangle in space. So I'm looking for that distance here. Now we know that this is going to be, given theta, an angle between n and PQ, this is going to be the norm of PQ times cosine theta. This is norm of PQ cosine theta. So this is what we're looking for. What's interesting is I recognize this kind of expression from a formula we've seen recently. We've seen that when we do PQ dot n, it's equal to the norm of PQ times the norm of n times cosine theta. And therefore, if I divide by n, I will get norm of PQ cosine theta equals PQ dot n over norm of n. And that is what I'm looking for. It's exactly the distance. Distance between the plane, let's call the plane pi, and the point Q. So this plane is pi. Pi seems like a reserved name for the constant, but pi stands for P, the letter P in Greek, so it's a convenient letter to name planes. So this is why the distance between a plane and a point, or a point and a plane, is PQ dot n over the magnitude of n. Secondly, let's see the situation where we have a line, and again we have a point Q that is not on the line. We will again want to find any point P, it doesn't matter which one, provided it's on the line, and we will again refer to the vector PQ. Now for lines, we don't have normal vectors, we have direction vectors, and in this example it's called U, so let's stick with that. Just like before, when we talk about the distance between a point and a line, it means the shortest distance, so it would hit here at a right angle, and what we are looking for is that. Interestingly, this is in fact norm of PQ times sine theta, where theta is the angle between the direction vector and PQ. Now I remember another formula that involves this piece of expression, and that is PQ cross U equals magnitude of PQ, magnitude of U, sine theta. And therefore, since I'm looking for PQ sine theta, I'm just going to divide by magnitude of U. So PQ sine theta, which is what I'm looking for, is equal to the magnitude of the cross product of PQ and U over magnitude of U. So that is the distance between the line L and the point Q. Let me call this line L. So these are really nice little visual proofs of how these formulas, why these formulas are true. Okay, so if you didn't copy the sketch that was shown in on the iPad, you can copy this and that. And now we'll finish with two very easy example. What is the distance between this point here and that plane? We just plug in the values and we get 4 over root 29. We just need to find one point that is in the plane that's required in order to find PQ. So you can choose whatever you want. The easiest is to select y and z equals 0, for example, which will yield x equals 4, hence the point 4, 0, 0. And then similarly, what is the distance between the point that was given above and the line here? Don't be fooled by a point here on the line. We want a point on the line, and it's ideal to just take the point 2, 1, something. That something is 0. Be careful, don't be trapped. It's not really intentional. It's not intentional that we try to trip you here. Just be careful. This here is 0 plus 2t. Okay, so the point is 210. So again, we plug stuff in, and we find that the distance is root 341 over root 21. So that's it for today's notes. Thank you very much.